Alrighty, we have here some examples of ways of trying to convince people of things that are true that aren't. Okay. Misleading graphs. You might even do it by accident. So the first one is an example of pay increases. These are the percentage of pay increases for 3 different groups of workers. The first group gets about a 7% pay increase, the second one a little bit less than 7, the third one just about 8. And you notice that we started this graph down here at 0%. So this area is proportional to the extra money you might get. So you'd say to yourself, okay, well, 6, 7, 6 1/4, 8, similar. Looks similar. Here, since I don't start at 0, I started more or less at 5%, so we're basically cutting this off like this. I don't know if I did such a good job. I think just kind of chop this here. And you only draw the thing that's from here on up. What that's going to do is accentuate those differences, which are minor, to make it look like this one had twice the raise of this one. That looks twice as big as that, but overall it's not twice as big, it's a little bit bigger. So that makes you, if you want to make a case that Group B is being underpaid, you would draw this graph. If you want to make the case that Group B is getting about the same pay increases as everybody else, you would make this graph. And that's really the truth, because this starts at 0, so this height represents the total pay increase. This height doesn't. You'll see those kinds of graphs. Sometimes I'll draw those graphs just because the bars are so similar, you want to concentrate on the differences. You have to be careful when you look at graphs. So the moral of the story is size should match amount. Here's another example of size not matching amount. Here's a couple bars where it does, because the height of the bar, the widths are the same. The one height is twice as big as the other. But then again, if instead of making bars like that, you made boxes like this, where the height and width were that same value, then this 4x4 box and this 2x2 box wouldn't look twice as big. It would look 4 times as big. So you're accentuating the differences by drawing a graph where the thing itself, when at the two values, the size of the thing doesn't look to be the ratio. The ratio of the values is not the ratio of the sizes. So sometimes what they'll draw, maybe I'll have trouble now. To draw like a person, I'll just draw something that looks halfway like a person. There we go, like that. And they'll say, okay, so here's the person. This is the 2-foot high person. And then we'll draw the same thing with 4. Good luck with that. And then we try to draw that. Of course, the person may be twice as big, but you don't see the height, you see the area. And if you imagine the person, maybe you think of the weight. So this looks a lot more than twice as big as that, if you're trying to make a case. Another thing you can do to mislead people is to change your categories in a way that it automatically favors certain categories to collect more values. So these are, what is this about? This was about Lyme disease. Yeah, Lyme disease. So here are the age groups that they recorded incidents of Lyme disease. I made up these numbers. 5 cases between the ages 15 and 20, 10 for 20 to 30, 10 for, so notice these are actually matching the number of years, haha. So you would think if you're collecting cases of Lyme disease over people over a 30-year span, there could be a lot more people between 60 and 90 than in 15 and 20. And so naturally there's more cases. So here the case says, it looks like mostly old people get Lyme disease. Well, maybe it's mostly true. Right, here's 50 cases. Here's 25 cases. But wait a second, that's 50 years. Of course, they are old people. 40, I don't know. And this is 25 years. So it's to get twice the age group here as here, and there's twice as many cases. So the chance of having Lyme disease in a given age group seems like it's the same for every age. There's just going to be more people here and less here. So less Lyme disease, more Lyme disease, but not more frequency of Lyme disease. So the moral of the story is maybe we should graph the case rate. The case rate is number of cases divided by number in the category. So you'd count how many people were aged 15 to 20 and divide that into the 5 cases to get a rate per person. How many, for each 100 people, how many cases of Lyme disease do we see? 1, maybe? And we do that for all the categories, and then we could draw a bar graph of that, and it'd be fair. This is not fair because we're more likely to have more people in these bigger groups, and therefore more likely more cases. And so that's a misleading graph. It makes it look like older people tend to get Lyme disease more readily than younger people. It's just that we're counting more people there, and so we see more cases. Another thing that can go wrong is you're using a count or a percent, and you're using the wrong one. So here's a case where we were looking at drivers over 50. So drivers, I want a better color. Drivers over 50. In our particular location, there were about 154,000 drivers over 50. And this is drivers under 50. So there's basically 4 times as many drivers under 50 as over 50. And then we look at the number of accidents, number that had accidents in the past 10 years. Well, it looks like the young people are about twice as accident prone as the old people. Twice as many. But wait a second, there's 4 times as many people. So do you expect them to have 4 times as many accidents if they're just as accident prone? So this is unfair to think the young people are causing all the accidents. There's more young people, so they have more accidents. It's like up here with the Lyme disease. Now, if we did a percent instead, so if there's twice as many accidents, but 4 times as many people, the accident rate is actually half as big for young people as for old people. So if we took the number of accidents, which I guess is like 25,000, and we divided, or if this is going to work, and we divided, I don't know if these bars are the right height for that. If there are, think about it, 25,000 accidents, I have to get my calculator out. We want to take 25,000 divided by 66,000. I think it's something like 4%. It should be like a 4. That's probably more like an 8. I'm guessing now, maybe here. 4 and 8% might be the right numbers. But now when we flip this around, then it looks like this one's twice as many. It's the same data. You have to think, do we want to count how many accidents? Is it fair for if there's 600,000 young people to say, well, look, you did have 25,000 accidents, the old people only had 12,000, so old people are better drivers? Or do we go over here and say, well, look at this. The 10% of old drivers had an accident in the past 10 years, and only 4% of young people had an accident, so young people are better drivers. You see the problem? This stays more fair. Not fair here. More fair here, that's my guess. So lots of times the rate is the way to go and not the amount. So beware when you see a graph of counts, when you're coming out of populations at different sizes and you're wondering how many of something happens, and you're comparing counts, is that really the right thing to do? So there we go. That's some misleading graphs. On the next slide, we're going to see some example, more misleading graphs, and some I'll go over some of the slides taken off of the internet that show pictures of news and weather reports on television. These are real. You look at them. They're real. They're real. These aren't made up. Some of them look kind of made up because I think they're just some of them are kind of a joke, but only maybe one of them. All the rest of them I think were, well, most of them were real news reports. If you watch news carefully after you've been through a stats class, you go, hey, that's not how you should do that. I don't even think you did it on purpose. I think you just did something crazy because you don't know how to make a graph. And there you go. We'll talk about those in a minute.